Hi, I'm Santiago Romero, a mechatronics engineering major at Kennesaw State University, and I'm currently working on a project of creating an electric pickup for my Physics 2212 class. Although an electric pickup sounds like something a Detroit automaker would come out with in the next couple of years, I'm not referring to an electric pickup truck, but rather an electric guitar pickup. Electric pickups were the last among a line of inventions with the goal of amplifying a string instrument's sound in order to be better heard within bands, orchestras, and alongside brass instruments. Some notable examples of these inventions include John Doiber's and George Beauchamp's resonator guitar, or George Reed's 1890 patent of a guitar which used a magnetic field to continuously vibrate the guitar strings, forming an instrument more similar to a violin or other bowed instruments. And although the official creation of the electric pickup is often attributed to Gibson's Lloyd Loar, research has led me to believe that the true first electric pickup was created by the Electro String Company under the leadership of George Beauchamp sometime in the late 1920s. The first electric pickup. The electric pickup consisted of two permanent horseshoe magnets in a wound coil around 6 steel poles, with each pole sitting under a guitar string. The electric pickup was eventually placed in the Rick-Baxter A22 Electro Hawaiian, more commonly known as the frying pan. Although quite crude looking, this design was later refined into what became known as the single coil pickup, it made commercially successful by the then named Gibson Guitar Corporation and Fender. Motivation. Although I'm majoring in mechatronics engineering, had it not been for COVID-related lockdowns, there's a fairly good chance that I'd currently be interning at Gibson. Back when I was in high school, I was instructed by my music tech teacher Andrew Edwards to create an electric guitar pickup winder, as he had the goal of creating a Stratocaster with fellow students. I spent the next 6 months designing, 3D printing, and wiring a pickup winder with spare parts, chips, and a motor from a broken hairdryer. When this was finally finished, the design caught the attention of Gibson as I had designed a machine that commonly sells for $300 to $500 for $20 in scrap. As a result, I, alongside other students, were invited to the Gibson factory in Nashville, Tennessee, which had been previously closed for tours for the past 20 years. With the condition of my going being that I stopped skipping class until the trip. What can I say? I was a senior and I was already accepted at Kennesaw. Although the trip never came to fruition as a result of lockdowns, I saw this project as an opportunity to finally be able to use the machine I built, create a fully working pickup backed by scientific research and mathematics, test the pickup by wiring it into a guitar, and hanging out with my music tech teacher. Problem statement. Although single coil pickups have been produced for years and become iconic for their uses in the Fender Stratocaster and Telecaster, their design and balance have been historically geared for the heavier styles of playing popularized in the 1970s. This has led many pickups to be designed and wound in what is often considered a hot configuration. For single coil pickups, this often means they are designed with the goal of a resistance of around 10,000 ohms and inductance of over 3 henries, leading them to be louder and more full in tone, but result in a pickup that's more sensitive to outside interference. The opposite configuration is known as vintage or cool, which often aims for a resistance of around 5.5 thousand ohms and inductance of less than 3 henries. This leads them to be quieter and clearer sounding, but less likely to suffer from interference. The pickups are commonly used for blues and a more classical style of guitar. However, pickups are often mislabeled by manufacturers, including Fender, thus leading to pickups being used for the wrong genres. A great example of this are Fender's Vintage Noiseless, which have a resistance of 9.8 thousand ohms and inductance of 3 henry, making them sound closer to a hot configuration than anything. The aim of this project is to use the knowledge I've gained in Physics 2212 and various resources I've accumulated throughout my engineering career at KSU to mathematically deduct the best design for a vintage style pickup, create this pickup, and compare it to some commercially available pickups. Resources and limitations. Resources. I have a Grenda, my pickup winder, 42 AWG wire, a pickup kit for Strat from StuMac.com, a Fender Tex-Mex metal pickup, a Stratocaster style guitar, a 6.3mm jack, a set of Husky digital calipers, a Klein Tools multimeter, wire cutters, electrical wire, various resistors, 9-volt AA and AAA batteries, a stopwatch, and a camera. Limitations. No way to generate an AC current. No way to directly measure inductance. No way to measure the strength of a magnetic field. The setup will be designed with these resources and limitations in mind. Setup. Although pickups are often advertised with certain resistances and inductances, these figures need to be generated by vibrating a magnetized guitar string or strings over the pickup, which generates magnetic flux, which generates a change in magnetic flux, and creates a current through the inductor. However, what is not publicly known is what distance away from the pickups manufacturers set their strings to when finding these pickups. The first step in this project is to find what distance away from the pickup a string needs to be set at in order to get a pickup's advertised resistance and inductance. To do this, we'll be using Fender's Tex-Mex pickups, which have an advertised resistance of 6.4 thousand ohms and inductance of 2.75 henries. I'll be using an electric caliper to determine the pickup's distance away from the string before strumming the guitar and measuring the voltage and current in order to calculate resistance. This will be repeated until an adequate distance is found that demonstrates results in line or approximate with advertised resistances. Store this value distance, store this value resistance. This distance will later be used as the distance the custom pickup should be away from the strings in order to properly test and accurately find its resistance. This will allow for a fair comparison between the custom pickup and manufactured pickup. Considering that we are aiming to make a vintage pickup, we'll be aiming for a resistance of around 5.5 thousand ohms. However, before we get on to how to calculate this theoretical resistance of our custom pickup, first we need to talk about how to determine the inductance of a pickup and determine how to calculate the necessary characteristics of our custom pickup in order to hit the value of its theoretical inductance. Although I have a fairly accurate way to determine and calculate resistance thanks to my multimeter, I unfortunately do not have an accurate way to measure inductance. This for the most part requires an LCR meter, which go around for $50 on the low end. However, I believe this is a great opportunity to use the knowledge I've gained in Physics 2 in respect to Faraday's law and the various formulas derived / based upon it in order to determine and calculate inductance. Considering we have a multimeter at our disposal, we'll be able to confidently find voltage, current, and resistance. However, what we can also measure is change in current over time. To do this, we'll be creating a series circuit with a AA battery, the pickup, a switch, and a multimeter. At the same time, we'll be setting up a stopwatch to count the amount of time in seconds it takes for the current to max out once the switch is flipped. We'll then videotape / record the switch being flipped with a stopwatch and frame in order to determine the change in current over time. This value can then be used with the equation below to determine the inductance of the pickup. This equation will be used to determine the value of the manufactured pickup's inductance in order to compare it with the actual / experimental inductance of the custom / created pickup. The found inductance of the manufactured pickup will then be inserted into the equation for the inductance of a solenoid, which is what a pickup is, in order to determine the number of turns of wire the pickup is made up of. Store this value. Using this equation, we will then begin to work backwards. Considering we're aiming to make a vintage style pickup, we'll be aiming for an inductance of around 2.5 henries. However, this could change slightly depending on formulation. Using this as theoretical inductance, we will then plug it into the equation below in order to determine the amount of turns necessary to generate this value. Length and area will be calculated using the previously made pickup base. Store this value. With the number of turns determined, we will then return to how to calculate the theoretical resistance. Resistance in the inductor is determined by the amount of resistance and the length of wire used. Thus, the formula below should return the theoretical resistance of our custom pickup, considering we're aiming for an inductance of 2.5 Henry. With A being the cross-sectional area of the wire, L being the length of the wire, and P being the resistivity of the wire. Considering we're using 42 AWG wire, resistivity should be that of copper, and the wire's radius should be 3.302 times 10 to the negative 5 meters, which can be used to calculate the radius, or the cross-sectional area. To determine the length of the wire, we'll be using the formula below, with minimum length being the length from magnet 1 to magnet 6 in the manufactured pickup, and max length being the length from end to end of the manufactured pickup. If you like, you can pause to read the notes and disclaimers I have based on this mathematical theory. With the number of turns being the previously stored value. You can then solve for the theoretical resistance of the custom pickup using the data found up to this point. Consider we're aiming for a resistance of 5.5 thousand ohms. If this theoretical resistance is not around that value, either a new setup should be developed in order to reach the goal of both an inductance of 2.5 Henry and a resistance of 5.5 thousand ohms, or new goals should be established. However, if both these goals have been approximately met, we should now have all the information needed, number of turns, in order to create a custom/vintage pickup. This will be done with Grenna, the pickup winder I built for my high school. Experimentations and problems. 1. Finding the distance the pickup should be away from the strings. Discovery. Considering that resistance doesn't seem to increase or decrease consistently over time within distances of 3.18 millimeters to 6.68 millimeters away from the strings, it can be determined that both voltage and current are affected in the same proportional way based on the distance away from the strings, and thus that regardless of distance within these parameters, a resistance close to advertised will be reached. Thus, the most important measure for determining which distance should be selected changes from the distance at which the advertised resistance is most consistently read to where the resistance is most consistent. Resistance is shown to be most inconsistent between 4 millimeters to 6 millimeters away from the strings. Thus, distances between 3 millimeters to 4 millimeters away and 6 millimeters to 7 millimeters should be used. Looking back at it, it seems a little dumb that I believe that resistance would be heavily affected by the distance the pickup is away from the strings. The only thing that would be affected is voltage and current, as resistance would be a constant regardless of the distance, because nothing is physically changing within the pickup. However, this is a great opportunity to see Faraday's law of induction at play. According to Faraday's law of induction, EMF, also known as voltage in this case, is determined by N, the number of loops. The number of loops multiplied by the change in magnetic flux over time. And in this case, the reason why the voltage, thus EMF, increases as distance decreases is because the closer you bring the pickup to the magnetized strings, the greater the density the magnetic field lines becomes, and thus when the strings vibrates, leads to an increase in change in magnetic flux. Just cool to think about. Chosen distance, 3.5 millimeters away from the strings. 2. Finding the inductance of the manufactured pickup. Discovery/problem. As stated in the setup, I had originally planned to use the equation related to I of t in order to solve for the real inductance of the manufactured pickup. However, when I first solved for L, I was returned a value of 1,339.5 Henry, almost 500 times the advertised value. Confused, I started researching the problem with my answer. Many online resources I found stated that the equation I was using to solve for I of t worked for an ideal/perfect inductor. That is, an inductor with no built-in resistance. However, because this inductor has an advertised resistance, and not just any resistance, but a resistance that is 24,000 times larger than its advertised inductance, the time it would take for the inductor to act as a wire would be incredibly small. This led me to research different ways to calculate inductance while keeping my limitations in mind, and find that solving for inductance in relation to power might be more efficient. In attempting to solve for inductance in relation to power, I was determining an inductance of 86 henries, smaller than 1,339, but still way too large for a company as large as Fender to chalk up to a manufacturing mistake. Finally, using the same formula, I decided to solve for current with the advertised inductance of L, just to see what kind of result I would get. Confused, considering the current originally used to solve for L was only off by about 0.002 milliamps, I plugged this current back into the equation in order to solve for L again, which returned an inductance of 3.03 henries, which is much closer to the advertised inductance. Here's where I realized my true problems. Although I believed that the amount of time it would take for the inductor to act as a wire would be incredibly small, I had no way of determining its actual value, as the amount of time it would take for the inductor to act as a wire would change between pickups. This prevented me from attempting to solve for t in the equation related to I of t, as t is a variable that's constantly changing. Thus, I would only be solving for the time it takes for one specific pickup to hit one specific current. Seeing this goal is to find a way to compare the real inductance of the manufactured pickup to that of the custom pickup, there's no point in solving for this t, thus forcing me to continue to use 0.85 seconds as t, as it was the only value for t I had, and hoping that when solving for inductance in relation to power, I wouldn't have any issues. Problem number 2. What solving for inductance in relation to power made me realize is that as a result of having such a massive resistance to work with such a low voltage, the current the multimeter would have to show would have to be incredibly accurate, within less than 0.001 milliamps, in order to find the real inductance of the manufactured pickup. Worst of all, this difference of 0.002 milliamps turns out to be almost the exact amount of tolerance my multimeter is rated for when measuring in terms of milliamps, thus showing that regardless of how hard I try, I'll never be able to get values this precise with my multimeter. Problem number 3. I no longer have any tools to work with in order to solve for inductance. The only other way I can think of to solve for inductance involves the two formulas below, one of which requires an AC power supply in order to regulate frequency, and another which requires a Gauss meter to measure magnetic fields. Nonetheless, even with all these issues, I still needed a way to at least estimate the real inductance of the still-to-be-made custom pickup. Thus, I made a hypothesis. Hypothesis. At least in relation to pickups, inductance can be approximated with either a linear or polynomial function in relation to resistance. Research. Going through Fender's website, I compiled a list of every pickup they offered for sale and noted their advertised resistances and inductances. I then organized and created a chart in Excel with resistance increasing from lows to highs on the left and their respective inductance on the right. Using this chart, I then created a scatter plot with the following points. Removed what I believe to be outliers before recreating the graph. Looking at this graph, I assumed that the most accurate equation for a trend line to describe the graph would be a simple linear equation. However, this only gave me a r-squared value of 0.7164, which I would argue could hardly, if barely, prove my hypothesis. Thus, I switched to the polynomial equation. This polynomial equation resulted in an increased r to the power of 2 value of 0.8244. But considering the best fitting trend line so far was a polynomial to the power of 2, I decided to reintroduce what I had previously believed to be outliers in the graph. This resulted in a trend line with an r-squared value of 0.9009, which could definitely be used to prove my hypothesis. You see, the reason why inductance increases with respect to resistance is because these are quadratically proportional, at least in the case of a pickup. Resistance to the solenoid is calculated as a function of length times resistivity divided by cross-sectional area. This means that while using only one type of wire, as length increases, so does resistance. On the flip side, inductance of a solenoid is calculated as a function of mu naught times number of turns squared times area of the core divided by length of the solenoid. But you see, pickups have a lot of constants. 42 AWG wire is almost universally used in single coil pickups, with its next closest competitors being 41 and 43 AWG wire. This means that the cross-sectional area in the resistance formula is almost certainly a constant throughout all these pickups. Resistivity has always been a constant considering it varies on material, with copper almost universally being used in single coil pickups, thus denoting resistivity as 1.77 times 10 to the negative 8 throughout all these pickups. Lastly, area of the core and length of the solenoid are industry standard, with very small variations considering the core is made of magnets that need to sit under the strings in order to magnetize them, and that if the length of the pickup is too large, it would not fit in an electric guitar. The only real variables in an electric pickup, unless you decide to use 41 AWG silver wire, are the number of turns the wire does around the solenoid, which then increases length, and the length of the wire, which increases the number of turns around the solenoid. Moreover, considering the number of turns is squared to calculate inductance, while length is not squared to calculate resistance, means that it makes sense for the equation used to determine inductance in terms of resistance to be a polynomial to the second power. Of course, this is not perfect. Even in the best case scenario, only an r-squared value of 0.009 is reached. However, considering our limitations, this is the best we have to work with. 3. Determining the number of turns needed to hit an inductance of 2.5 Henry. The first step in this process is to calculate the number of turns used in the manufactured pickup and ensure that they are a reasonable number using the formula below. L would be 2.75, length would be 10.77 millimeters, and area would be calculated as the area of the stadium using the formula below. This area can then be plugged into the previous equation to determine the number of turns. 9,370 turns is fairly reasonable, although I did expect it to be a tad lower. However, just to demonstrate how unreasonable this value can become, I'll be using the incorrect inductance of 83, which I had previously found using the formula of power in relation to inductance. 52,492 turns is unreasonable. Now we will solve for the number of turns needed to reach a hypothetical inductance of 2.5 Henry for a custom pickup. 9,039 turns would hypothetically work just fine. However, considering that I built Brenda the pickup winder while I was in high school and before I had any coding knowledge, it has a couple of limitations of its own. One of these limitations being that it can only count and automatically stop in intervals of 1,000. Thus, instead of 9,039 turns, we'll be using a clean 9,000. The theoretical inductance for this is demonstrated below. An inductance of 2.48 Henries. 4. Determining the custom pickup's preliminary theoretical resistance. As stated in the setup, the first step is calculating the total length of wire used, using the formula below. This length is then plugged into the formula below with a cross-sectional area of 42 AWG wire to calculate the custom pickup's preliminary theoretical resistance. Considering we know that the amount of turns necessary for reaching an inductance of 2.48 Henries and a resistance of 5,765 ohms, I'd say we hit the characteristics of making a vintage pickup with an inductance around 2.5 Henries and a resistance of around 5.5 thousand ohms. Especially considering once the pickup is made, it should have a smaller min length plus max length divided by 2 value, considering less wire should be used compared to the manufactured pickup. Creating the pickup. Although I made Brenda the pickup winder, and thus am allowed to borrow it, some more basic tools required to make a pickup belong to my old high school, and as such I was required to return in order to make the pickup. Some of these tools include a drill press, strong neodymium magnets, a Mojo tone hand-guided tensioner, and various guides. The steps for creating a single coil electric guitar pickup go as follows. And here are a couple videos showing the process of making the pickup. With the pickup now finished, I'll begin testing it using the methods illustrated in the setup for finding the real resistance and inductance of the manufactured pickup. Step 1. Finding the pickup's experimental resistance. In order to find the custom pickup's experimental resistance in a way that can be fairly compared to the manufactured pickup, we want to recreate the same environment the manufactured pickup had during testing. However, before we do so, note all the dimensions of the custom pickup with specific importance on the min length and max length. Then I install the pickup into the guitar as can be seen below. I simply unscrewed the manufactured pickup from the pickguard, cut its wires, and rewired the custom pickup in its place. I then tested that it was outputting a signal by tapping on the magnetized rods with a screwdriver. Hearing a thunk coming from all the pickups through the amplifier, I justified that it was correctly installed. I then restringed the guitar using new strings and set the pickup at a distance of 3.5 millimeters away from the strings using the digital caliper. I then strummed the guitar while having the multimeter connected to one end of the 3.5 millimeter jack, with the following end plugged into the guitar and noted voltage and current, giving the following chart. When compared to our preliminary theoretical resistance to solve for percent error, we receive a percent error of about 24.02%, which, all things considered, isn't too bad, especially considering this was done with our preliminary theoretical value for resistance. Now with our custom pickup finished and its dimensions noted, we can more accurately find the theoretical resistance with the method described in the setup. Using the dimensions of the custom pickup, we will return to secondary and more accurate theoretical resistance, which when used to determine percent error, returns a percent error of 21.66%. Still a tad bit high, but it goes to show that the preliminary theoretical resistance was already fairly on target. Nonetheless, a resistance of 4,380 ohms still falls within target of a vintage pickup. So thus far, it appears to have been successful. The reasons for why this percent error could be so high will be explained in the results. Experimental resistance, 4,380 ohms. 2. Estimating the custom pickup's inductance. As previously stated, we have no way of determining the pickup's inductance, as my tools are either too inaccurate, the amount of time it would take for the pickup to act as a wire would be too small to measure, and/or the fact that I have no way of generating an AC current. Thus, by creating a scatter plot with various other pickups' resistances and inductances, and generating a trend line, I determined the formula for calculating the pickup's inductance in relation to resistance to be y equals 0.0247x to the power of 2 minus 0.305x plus 3.7278, with y being inductance in henries and x being resistance in coulombs. Using this formula, I plugged in our experimental resistance and we returned an inductance of 2.86 henries, which, when compared to the theoretical value of inductance of 2.48 henries to calculate percent error, returns a percent error of 15.32%, which, to be quite frankly, is pretty darn close to our theoretical value, and still falls below the 3.4 Henry limit, which defines it as a vintage pickup. Experimental inductance, 2.86 Henry. Results. Results. Experimental resistance 4,380 ohms, experimental inductance 2.86 henries. Overall, the experimental results from the custom pickup fall within vintage pickup standards, and thus I believe this project to be a success. However, there are some caveats with calling this project a complete success. Our true experimental Henry is most likely less than 2.75 Henry. Considering the formula for inductance of a solenoid is as follows, in that the experimental inductance of our custom pickup is higher than the advertised inductance of our manufactured pickup makes no sense. We previously found that the amount of turns in the manufactured pickup was around 9,370. So then how did we receive an inductance that is higher than the manufactured pickup while using less turns? My theory is that the equation for the trend line, which solves for inductance in terms of resistance, grows more and more inaccurate the further we get from pre-established, thus confirmed data points. Looking at the graph, the pickup with the lowest resistance is rated at 5.6 thousand ohms. Then plugging a resistance in that is about 1.2 thousand ohms lower most likely means that the inductance we're being returned is inaccurate. Then another question arises. Why was our custom pickup's experimental resistance 1.2 thousand ohms lower than its secondary theoretical resistance? I believe this to be a result of machine error. My pickup winder Grenda was built as a high school project and was kept in storage since the start of COVID almost 3 years ago. Moreover, when it was just finished, it suffered from problems that are still plaguing it today. For example, the Hall effect that is used to increase the counter almost always skips forward at lowered speeds. In addition, my winding job is not necessarily perfect, considering loose wires can be seen in the picture below. Conclusion. Although single-coil pickups have been produced for years and become iconic for their uses in the Fender Stratocaster and Telecaster, their design and balance have been historically geared for the heavier styles of playing popularized in the 1970s. This has led many pickups to be designed and mounted in what is often considered a hot configuration, even though they are being marketed as vintage-style pickups, thus resulting in incorrect pickups being used for certain genres. This research paper aimed to create a truly vintage pickup backed by the knowledge we have acquired throughout our time in Physics 2 and my available resources. This resulted in the usage of various tools, machines, formulas, and analytics in order to determine how to best make said pickup and then compare it to its theoretical characteristics in other commercially available pickups. I believe this knowledge can be used by fellow guitar makers in order to better understand the science behind their passion and help them refine pickups they seek to make in the future. Thank you.